So if we pick on, say, the third column or something, then factoring out a C gives me a DH minus EG, which happens to be exactly the 2 by 2 minor, the determinant of the 2 by 2 minor matrix that we get from C. And then when I take an F out, I end up with BG minus AH, which is not exactly, which is not exactly the determinant of this 2 by 2 matrix, but it's rather the opposite of the determinant of this 2 by 2 matrix. So you notice that that pattern continues as we move around the matrix. If I factor the I out, I end up with AE minus BD, which is exactly the determinant of that 2 by 2 minor of the entry I. So how to know when we need a plus in front of the determinant and when we need a minus in front of the determinant of a relevant minor was where this matrix of pluses and minuses came in that I had you do at the top of the second page. Right? Just to say that whenever I'm choosing an entry and looking at its minor, I'm going to either preserve its sign, if there's a plus here, or reverse its sign, if there was a minus here, when I'm writing out a cofactor expansion. And the cofactors themselves, so just to take apart the word really quickly, cofactor is something that goes along with a factor in an expression. And so if I'm computing a determinant via a cofactor expansion, let's take your first column cofactor that you did for number, well, you might have done it for number 7. You might have chosen a different technique for number 7. But if we write this entire determinant out for number 7, what did it look like?
The whole thing, or just
The whole, well, let's just start with 1 times what?
2 times 5
Right, you had 2 times 5
minus 0 times 0.
minus 0 times 0, followed by 6 times
3 times 5 minus negative 2 times 0.
negative 2 times 0. Okay. And finally, right, move this up here. And finally, 9 times
3 times 0
3 times 0
minus negative 2 times 2.
negative 2 times 2. And then, based on these pluses and minuses in the first column of this matrix of signs over here, we would put a minus sign on the 6. And then we would add these results all together. And so the terminology of cofactor comes from the fact that we're calling the 1, the 6, and the 9 here, these are called the factors, the things which we are multiplying. And then each one of them has the corresponding thing that we're multiplying it by, which is called the cofactor. So the cofactor of 1 is 2 times 5 minus 0 times 0. It's this product right there. The cofactor of 9 is this determinant right there. And the cofactor of 6 includes not just the 3 times 5 minus negative 2 times 0, but it also includes that secret little negative 1 that's sitting out in the front. So it turns it negative, right? If we simplify what we have in the blue boxes over here, 2 times 5 minus 0 times 0, better known as 10. And so 10 is the cofactor of the number 1, which is why in this matrix of cofactors you put it right there in the first row, first column. Then when we simplify out the second determinant here, 3 times 5 minus negative 2 times 0 is 15. But then we account for that negative sign out in front, we make that part of the cofactor as well. And so the cofactor of 6 in this matrix was negative 15.
So if you had originally gotten a negative 15, it would have become positive.
It would become positive 15, right. So the sign either stays the same or it flips. So think of this as same or flip matrix. And the cofactor of the 9, 0 minus negative 4, gives you a 4. Sorry, let me fix that. We were going down the first column. So going down the first column, so those cofactors belong in the first column. There we go. That makes me feel better. And then finding the cofactors of everything else. What did you get going across the top row? So first row, second column? Negative 30. How about first row, third column? Negative 18. Middle entry, second row, second column? 23. And second row, third column? 27. All right, finishing the last row. Negative 12. Negative 16. Okay. So here we have all 9 of the cofactors of our matrix that we started with. And the real big finish happened when you took that matrix of cofactors, you turned it on its ear. So you took its transpose, 10 minus 30 minus 18 minus 15, 23, 27, and then 4 minus 12 minus 16. And then you multiply that by the original matrix A. So make some room here. And I multiply that by A. And what happened?
All zeros negative 44.
Right. We got a matrix that had a whole bunch of zeros in it, and the only places it didn't have zeros was on the diagonal. And what was on the diagonal? Negative 44. Which just so happened to be, what was negative 44 in this problem? Yeah, namely, it was the determinant of our matrix A. No matter which cofactor expansion we use to find it, that's what it was. And by the way, somehow this shouldn't be too much of a surprise, because look at where that first negative 44 comes from. This negative 44 right here in our answer. Well, that would have come from multiplying the first row of the first matrix here by the first column of A. But what are we doing when we're multiplying that row by that column? We're exactly getting 1 times 10 plus 6 times negative 15 plus 9 times 4. In other words, we're getting exactly the cofactor expansion that we built, which was a cofactor expansion down the first column. So it's not a surprise that we got the same answer as we got when we just computed the determinant up here using the cofactor expansion, negative 44. What's kind of surprising is that we get so many zeros in this matrix, because the entries on the diagonal are just exactly the cofactor expansion determinants down the first, second, and third columns of A when done this way. But the fact that all of the off-diagonal entries are 0 is the miracle. Because what this allows us to do is the following. And by the way, this matrix that we get by turning the cofactor matrix on its ear, this C transpose, is what we call the adjugate matrix of A. Adjugate of A. And when you multiply A by its own adjugate, we get a matrix which is almost the identity matrix. What separates it from being the identity matrix? It's multiplied by the determinant. So when you multiply a matrix A by its own adjugate, you get the identity matrix multiplied by the determinant of A. So let's, to finish, tease out the consequences of that. So if I write for the adjugate of A, ADJ of A, then the adjugate of A multiplied by A is equal to the identity matrix multiplied by the determinant of A. So what secretly does the adjugate help us to find? It helps us to find, well, it kind of helps us to find the identity, but we know what the identity looks like. What we don't know is what the inverse looks like. Exactly. So the adjugate is helping us to find the inverse. And to figure out how, let's get the identity by itself on the right-hand side of this equation. Because that's what we would need to see in order to find the inverse of A. We would need to find a matrix which, when we multiplied it by A, gave us the identity. But now, just dividing both sides by the determinant of A, we find out exactly what we need. It's the adjugate of A divided by the determinant of A. So the upshot of all of this is that the inverse of the matrix A is exactly its adjugate divided by its determinant. And this gives us a new way of computing the determinant of a matrix without doing any row reduction. So in place of doing row operations, we're computing the adjugate, which for a 3 by 3 matrix consists of 9 2 by 2 determinants. Not the end of the world, because each 2 by 2 determinant is not so bad. And then we just have to divide by the determinant of A itself, which is a 3 by 3 determinant. So the amount of work now that goes into computing the inverse of a 3 by 3 matrix with this method is the cost of 9 2 by 2 determinants and 1 3 by 3 determinant, and no row operations at all. So it just gives us an alternate way of computing the inverse using determinants. And you get a bit of a hint here as to why mathematicians went so crazy over determinants in the 19th century. Because they knew how to do a bunch of linear algebra before. They thought that determinants might be sort of the be-all, end-all of linear algebra. They figured out eventually they ran out of steam and abandoned determinants, as we're about to do in our course. But not before they did a lot of really neat things with them, and this is one of them.